It's literally the foundation of our world. It's under our feet, in our homes, our skyscrapers, our bridges. It is everywhere. But inside every single slab of concrete is this hidden world of, believe it or not, violent chemical reactions and incredible microscopic construction. Today, we're going to pull back the curtain and explore the surprising science of how concrete actually gets hard. So let's dive right in. So let's start with the big question. How does this gray, soupy sludge turn into something you can build a city on? You probably think you know the answer, but I promise you, the reality is way cooler than what you're probably thinking.
So, the number one myth, the one almost everyone believes, is that concrete just dries out. Like a mud puddle baking in the sun. The water just evaporates and poof, it's hard. But that's not what happens, not at all. The real magic is a chemical process called hydration. The water isn't just leaving, it's a critical ingredient that sparks a total transformation. To put it as simply as possible, this is not about water leaving the party. This is about water getting to work and building the house. It's a fundamental chemical change where water and cement combine to create entirely new rock-solid structures from the inside out.
Okay, this graph right here, this is going to be our roadmap. It charts the flow of heat, all that energy being released as a batch of cement hydrates over just 24 hours. And it tells this incredible story, a real drama in 4 acts. We're going to walk through this journey together, step by step.
Our story kicks off the very second water touches cement powder. And let me tell you, it's not a gentle mix. It is an immediate and surprisingly violent chemical event.
Take a look at the graph. See that first really sharp spike of heat right there at the beginning? That's the initial reaction, and it happens within minutes. This is the moment water hits the cement, and on a chemical level, things just go wild. So what's happening in that first crazy burst? Well, it's a process called dissolution. The surfaces of the cement grains instantly start to break down, releasing this flood of calcium and silicate ions into the water. This breakdown is exothermic, which is just a fancy way of saying it releases a ton of heat, and that's the spike we see on the graph. But then, just as quickly as it started, something really strange happens. After that initial chaotic burst, the entire reaction just slams on the brakes. A weird, deceptive calm falls over the whole mixture.
Right here on our graph, you can see the reaction rate just plummets into this deep valley. This is called the period of slow reaction, or the induction period. The concrete is still liquid, it's still workable, so the big question is, why? Why did everything just grind to a halt?
Well, the leading theory is something called the metastable barrier hypothesis. Now, in simple terms, what happens is a microscopic protective shield, this thin layer of a gel-like substance, quickly forms around every single particle of cement. And this shield, this passivating layer, physically blocks water from getting to the raw cement still hiding inside. This diagram shows us exactly what's happening at that tiny scale. You've got the unreacted cement in the middle, and these layers form around it. That semi-permeable layer is the key. It slows the whole process down to a crawl. And this quiet period is absolutely essential. It's the golden window of time that builders have to pour, shape, and finish the concrete before it sets.
But this calm doesn't last forever. Those protective shields, they're not stable, and eventually they break down. And when they do, the main event kicks off, the real race to harden, where concrete's legendary strength is finally born.
And we're back to our graph. Look at that reaction take off, creating this huge second mountain of heat. This is the acceleration period. The protective barriers have ruptured, and the hydration reaction just goes into overdrive, releasing a massive amount of energy. This is the moment the concrete truly begins to set and gain its strength.
So what's driving this? The core mechanism is a beautiful process called nucleation and growth. Think of it like making rock candy in sugar water. First, tiny little seed crystals, the nuclei, have to form. And once they're established, they just start to grow and expand like crazy.
So what is this stuff that's growing? It's a totally new material called calcium silicate hydrate, or CSH for short. You can think of this as the superglue of concrete. It grows in this dense, interlocking web of needle-like crystals shooting out from the cement particles. As these webs of crystals grow and get tangled up with each other, they form a rigid, microscopic scaffold that locks everything, the sand, the gravel, in place. And that is what creates the immense strength of concrete.
Now, after hitting that incredible peak of activity, you might think the job is done. But the work of building strength, it is far from over. The concrete is now entering a long period of maturation.
Following the curve down the other side of that mountain, we get to the deceleration period. The heat production slows way down, but don't mistake that for weakness. The concrete is still getting stronger. The reaction is just slowing because it's getting harder and harder for the water to find a path through that dense crystal jungle to reach any leftover bits of unreacted cement.
And here's the thing. While the most dramatic changes happen in that first day, concrete continues to get stronger for a very, very long time. That microscopic scaffold just keeps getting denser and more robust over days, weeks, and hey, even years, as long as there's a little bit of moisture still around.
Okay, so we've just witnessed this incredible microdance of dissolution. Shields going up, shields coming down, and massive crystal growth. It's fascinating science for sure, but why does it actually matter in the real world? Well, the implications are just huge.
This quote from the source material really hits the nail on the head. As we try to make greener, more sustainable concrete, using things like industrial byproducts and new additives, we're creating much more complex chemical cocktails. And to make those work, we can't just cross our fingers and hope for the best. We need to know exactly how this hydration dance works.
Because at the end of the day, by mastering this microscopic process, we can actually control it. We can design chemicals that make that quiet working period longer. Or we can design accelerators to speed up hardening when it's freezing outside. This knowledge is literally the key to engineering the stronger, more durable, and greener building materials of our future.
It really makes you wonder, doesn't it? Concrete seems so boring, so simple on the surface, yet it's hiding this incredibly complex chemical ballet. What other everyday materials that we totally take for granted are just hiding an entire world of fascinating science, just waiting for us to take a closer look?